So for the last lecture today, we have Patrick Allen, who will talk about automorphy lifting.
Hey, so thank you for the organizers of the invitation. And yeah, so my goal today is just to give like a broad intro and focus on a little bit on the specific example of like GL2Q, where things are easier, there's a bit of motivation and setup. So first thing I want to do is just talk about what are the goals. And let me just say right, the original and probably still principal, I mean, goal of modularity lifting is to prove cases of the following conjecture, which I'm going to attribute to Fontaine, Mazur, and Langlands, which is just if, let me see what it says up. So if F is a number field, and rho is a continuous representation, some p-adic vector space, finite dimensional. So let me say QP bar is continuous, absolutely reducible. Of course, I guess I don't need absolutely since I already took the algebraic closure. Continuous, irreducible, ramified at finitely many places. Duram above P. Yes, thank you for the reminder. Duram at P dividing P. Then it's automorphic. I.e., rho is isomorphic to some rho pi iota for some cuspidal automorphic representation pi of GLN del's over F. And iota will just be some fixed isomorphism between these two algebraically closed fields. Okay, so as I say, this is sort of the original goal and maybe the principal one, but there are other useful applications to the things I'm going to talk about. Some standard ones are special cases of the Bloch-Kato conjecture and also p-adic local Langlands. Some of the ideas that we're going to talk about in this are used in those cases, but I'm just going to focus on this. And today I'm even really going to focus on the particular case where this number field is Q, in which case when I say cuspidal automorphic representation, it really just means a classical modular form. Classical cusp form. Okay, and part of the reason why people we're interested in proving such things is, you know, natural consequences. We apply this to various arithmetic objects, right? Objects such as elliptic curves. Hence, you have things like analytic properties of their L functions, etc. Yeah, so these are sort of the principal motivations, these things. Okay, any questions about anything? Please feel free to interrupt. All right, so let's set things up a little bit further, talk a bit more about how we can do this. So you can assume, and Shinwen mentioned this in passing today by a bare category argument, right? You can assume our fixed rho actually takes values. Actually, wait a second, do I want to introduce some other notation first? Let me think. Rho, so its image lands inside GLN of O. So this will be my notation for some ring of integers for some finite extension over QP. Pi will be my uniformizer, and say K will be the residue field. Okay. So, but then we associate to this so-called residual representation. This will be rho modulo pi, which goes from gal bar over F to GL2K. Yeah, so this is. Oh, thanks. Yeah, thank you. The residual representation. Okay, and then basically the way one always proves a sort of a statement of this form, some sort of automorphy of some Galois representation, is it's in two pieces. The first thing you do is you try to prove the automorphy of this residual representation, and then you try to bootstrap, going from the residual representation, the original thing you care about. So I have these two steps. So one, prove rho bar is isomorphic to some rho bar not iota, or some hospital automorphic representation pi naught. So this is known as residual automorphy or Serre's conjecture. And then two, rho bar isomorphic to some rho bar pi naught implies rho is isomorphic to some or pi for some pi. And this is modularity lifting. Okay. And so what we're going to talk about in this sort of this mini course is this second step. So this first step actually nowadays seems to be in some sense the harder step. It's thank you again. Yeah. So this is really a stumbling block in general for proving the Fontaine-Mazer-Langlands conjecture. Is this residual automorphy or Serre's conjecture now? But it's worth mentioning maybe that even in the cases where we do know this, say GL2 over Q by Carré and Fontaine-Berger, the second step is actually a fundamental ingredient in this. There's some sort of induction process and bootstrapping going on here. Okay, so now let's say briefly, what's the idea of modularity lifting? Construct O algebras R and T such that, well, R, this would be some sort of deformation ring, sort of Galois deformation ring. Such that its homomorphisms, so the O algebra homomorphisms from R to, say, QP bar are exactly a sort of Galreps congruent to our fixed rho bar with certain local properties. Okay? And in particular, we construct this ring, whatever these local properties there are, to guarantee this contains our fixed rho bar that we start with, right? Our whole goal is we have some given rho that we want to prove is modular, and we're assuming it's residually modular. So we construct some sort of parameter space for all the things lifting this modular object and contains our given rho. And then we have T will be a localized Hecke algebra. Algebra, this is of some fixed weight and level. So constructed so that Hom, so O algebra Homs from T to QP bar are exactly fixed weight, whatever our fixed weight and level are, fixed weight and level Hecke eigensystems. Congruent to the one given by pi 0. Okay. And then we want to prove that these two things are isomorphic. And we construct a surjective O algebra map R to T and prove it's an iso. Or, I mean, what often happens in practice is maybe do it on maximal reduced quotients or something like this. T. Or in certain situations, you might do T red, or let me just say many variants of these things, whatever is sufficient for your purposes. Maybe you have to invert P, maybe take maximal reduced quotients, whatever. Okay. This is a general schema. Any questions here? Well, what I'm saying is, so in the original question, well, you want to, I mean, you do want to construct these things, say these, you know, these particulars R in some sort of very general way that can take points in any sort of complete local Noetherian ring or pro-Artinian ring or something like that. But at the end of the day, we hope it's just equal to a Hecke algebra of some fixed weight and level. So it's really just like, you know, some sort of order inside of a product of fields. And that this shouldn't actually be, although actually, sorry, I should say that, I mean, that's certain the situation for modular forms I'll talk about today, but in situations like imaginary quadratic fields, which James will talk about a bit more on Wednesday, maybe, then certainly there's interesting torsion phenomena here, and these a priori could even be entirely torsion things. Yeah. Yeah, right. So this is exactly such that this T is going to be some sort of Hecke algebra acting on some space of automorphic forms. And so it's going to be constructed, at least in this sort of classical picture, such that the QP bar points are really just given by eigensystems of whatever automorphic forms are in that space of fixed level you're looking at. And so your original row corresponds to some Hom from R to QP bar. And then that identifies via this isomorphism with a Hom from T to QP bar. And therefore, you get what you want. Yeah. Sort of basically, I'm going to take some sort of Hecke algebra, spherical Hecke algebra away from primes of ramification. And I'm just going to take the eigensystem of them acting on some sort of cospedal automorphic representation or some sort of eigenform in that space. Okay. Are there any other questions? Okay. So that's that. Yeah, but maybe actually just going back to something maybe it was earlier asked. So all this is in mind with this original conjecture as posed by Fontaine, Mazur, and Langlands. However, especially in the case of something like an imaginary quadratic field where these things should contain torsion, it's much, you get more and it's more interesting to just know if you actually have like an isomorphism from R to T. I mean, they may not even have any QP bar points, and there's still content, still interesting things here. You can say. Sorry? Yeah. Yes. Yeah, exactly. Yeah. Yeah, I'm not going to use the sort of ramified algebra stuff. But global, like everything here is global. Okay. So this is the intro. So let me start setting up a little bit of this info. So two, we're talking about R. So so let's get a little bit notation. So S will be a finite set of, let me say, finite places in F containing all the places. See, am I going to regret this? Let me say finite set of places. I'll throw the infinite places in here. P dividing P, also P dividing infinity, and the ramification set of our fixed row bar. So I'm going to consider this thing fixed. Right? It's going to ramify finitely many places. So, and I'm going to let GFS equal Fs over F with Fs equal to maximal extension unramified side S. And am I running out of room? I'm running out of room. Okay. So let me let C of O be the category of pro-Artinian local O algebras with residue field K, my fixed finite fields. And so a lifting of rho bar to some A, since it's C of O, is exactly what you think it is. Continuous, so it's a continuous Hom. Such that when I take the same modulo of the maximal ideal of A, I get my fixed rho bar. All right, see enough? And then we say two things, rho and, sorry, let me call this, decorate this with the rho A, because I had some fixed rho before. So rho A and rho A prime are strictly equivalent if rho A prime is conjugate by an element that reduces to the trivial modulo of the maximal ideal. So it's 1 plus n by n matrices maximal ideal. All right. Yes. Oh no, these are pro-Artinian. So I'm giving in the pro whatever topology. Yeah. Yeah. So no, this is much easier. Okay. Yeah, I don't have to worry. I have no topological sort of worries here. Okay. And I should say, actually, it's convenient to sometimes enlarge this to the pro-Artinian things, but actually everything we're going to do, these you can assume these are Noetherian. So in fact, I mean, let me just write, example. Right. These are very simple. Right. Example A is something like, a power series ring in some number of variables. Well, I don't use K. Modulo some ideal. Right. This is really all you ever have to think about. Okay. Okay, and then a deformation is a strict equivalence class of liftings. Right, so it's like, You've basically forgotten the basis. The idea, which is the sort of thing you want to do, right? And trying to do an R equals T business, because the Galois representations that come to automorphic forms don't have a natural basis. So, fixing a basis is a very unnatural thing to do. Okay, so then the theorem is, this whole thing was introduced by Maser, and so is that the functor, right? This D box, this is the same box basically that Xin-Wen used earlier today. Although since I'm working locally, I mean, this is a much easier, on this type of category, this is a much easier thing. It just sends A to the set of liftings. Things of bar to A. This is representable. And we introduce some notation for it. I'm going to call it our upper box, and it's called the universal lifting ring. AKA, since this terminology was used before, universal frame deformation ring. And Xin-Wen mentioned were the completed local rings of one of the stacks he was writing down earlier. And if the endomorphisms of my fixed row bar are just scalar, then the functor of deformations to deformations, sorry, I'll move this up. Deformations bar to A. Functor, this student is representable. Call it our univ, the universal deformation ring. Okay. All right, so this is the theorem. Let me say that the representability of the first is actually pretty easy, because all of these things, because these are pro-Artinian with this thing be a finite residue characteristic, up to this row bar, everything afterwards is pro-P. So you really just have to look at the quotient of the Galois group that is unramified outside. You take some finite extension and then take some maximal extension that's pro-P unramified outside finitely many primes. That's topologically finitely generated. So you can just create a ring with whatever finitely many power series variables there are, and then force whatever relations you want to make sure this thing is a homomorphism. But that's it, right? So this is actually quite easy. This is a little bit more work. There are many ways to do this, but one way you can see it is once you have this, you have an action of PGLN, formal PGLN on this. And this is telling you that it's acting faithfully. And then there's some general theorems that say if you have a smooth reductive formal group acting faithfully, you can take quotients. It's one way to see this consequence. Are there any questions here? While I move over here and raise some boards. Oh, that's the wrong side. Sorry, what's that? Oh, this strict equivalence is what I called. Sorry. I said the strict equivalence is basically conjugate by something that's congruent to 1 modulo the maximum ideal. Yeah. No, yeah. Yeah. For lifting, yeah, there's nothing. It's like, yeah. So this should say, I mean, this is sort of like, this is, I mean, the same, in some sense, the same sort of things came up in Shin-Wen's talk, where he was, distinguishing between modding by G-hat conjugacy or not. It's just that I'm saying if this happens, I'm literally in the situation where you don't have to care about stacks. This thing is really representable, right? Whereas, if you want to globalize things, as in Shin-Wen's talk, you have to, you're forced. You have to use the stack language. Whereas here, life is simpler. Okay. Okay, let's do an example. I mean, let's do the only example I can write down is if n equals 1. So in this case, my row bar is just a character. And for some reason, I don't like using row bar for characters. So I'm going to call it C bar, a character. And so let's let C from GFS to O cross be its Teichmüller lift. Okay, and let me say GFS abelian parentheses P equal to the maximal pro P abelian quotient of GFS. Then our univ is given by the completed group algebra for this. And the universal character, right? So by saying this is representable, right? We have over here, right, a universal lift or universal lifting, right? And if this is satisfied, we have a universal deformation. So what is it in this case? This is just GFS to cross. It's going to send sigma to, you take the Teichmüller lift, applied to sigma, and then with the Busen notation, I'll just write sigma, or what I really mean is the image of sigma inside the maximal abelian pro P completion. Okay, this is it. This is the universal character. Okay, right, and this because we know that this is, some finitely many copies of ZP in a finite group. This is then just some power series and finitely many variables mod some relations. However, let me point out that the number of variables involved in here, or rather the dimension of this ring, right? So notice then the dimension of this ring is exactly the ZP rank of this thing, and understanding that is exactly Leopold's conjecture. So although I can write this down, we immediately write down a very easy and fundamental question you could ask, which is what's the dimension of that is equivalent to Leopold's conjecture now. So, all right. Yeah, any questions? The dimension of the ring? Yeah, dimension of this ring, yeah. Leopold's conjecture. Yeah, that if you take units inside a numbering, that they're ZP linearly independent when you sort of map them inside the p-adic. Sort of the analog of the classic Dirichlet unit theorem. But you would do it p-adically with like p-adic logarithms, and the question is what's the ZP rank of that? And that's equivalent to knowing, what the ZP rank of the maximal abelian pro P thing on ramified outside things where you include P in the ramification set. Yeah, so let me just say as an aside, and what I think is at least an interesting non-abelian version of Leopold's conjecture is exactly a prediction on the dimension of these rings for higher rank then. Oh, yeah, these are formal. Yeah, exactly. This is represented really by a ring. I'm saying it's represented by an element of this category. And in the number field case, it's in fact always Noetherian. Okay. Yeah. Oh. Well, no, but I mean, basically the fact that it has to lift this thing, right, means it has to be congruent to it modulo P, or modulo the maximal ideal of any of these gadgets. So then it differs by the Teichmuller lift by something valued that's sort of inside 1 plus the maximal ideal. And so that's why this is this. If you forget this, that's the universal thing. Yeah, they're all specializations of this. That's right. What I'm saying is this is the universal object. So to get any lift at all valued in A, what you do is you just specialize this to, these things via some homomorphism. Yeah. Yeah. Okay. Good. Okay. However, for the purposes of modular lifting, this is too big. And you can see this here, right? If we want to try to understand Hecke characters here, some algebraic Hecke character, a fixed weight, has some fixed, inertia acts by some fixed algebraic character, right? So this is too big from that point. So we need to cut it down. And this is where we impose local conditions. Our universe is too big. And so now I'm just gonna, for the rest of the lecture, I'm gonna put myself in a not exactly simple, but simpler situation. So let's assume from now on, n equals 2, f equals q. I'm gonna also assume p is bigger than or equal to 3. Let's see, our pi naught is equal to the representation generated by a weight 2 modular form. G of level, I don't know, some gamma 1n, where the set of all primes dividing n is contained inside S. And I'm going to also assume P does not divide n. Okay, so let's put ourselves in that situation for the rest of the lecture. Did that go up high enough? It's okay. Okay, then my rho bar, right, which remember is now the rho bar G iota is something called finite flat, i.e. The rho bar restricted to, I would say GP will be my notion for the decomposition group at P. This is gal Q bar over QP is isomorphic to, and now for the conventions I like to use, I'm going to do something a little bit contrary, and I'm going to say the dual of the GP representation on a finite flat group scheme. Oh, sorry, generic fiber. Sorry. The GP representation on a finite flat scheme over ZP. Okay. Okay, so let me just say as an example, in case you haven't come across this before, I'm going to say something that essentially is just the definition, okay, but makes things a little bit concretely. So for example, if E is an elliptic curve with good reduction, your QP, good reduction, then this dual is finite flat with my convention, because I'm using dual just to, fit with things we're going to do later in the course. Use cohomological normalization. And this is just the definition, right? To have good reduction means it spreads out to an elliptic scheme over ZP. And so then we know that this is a finite flat group scheme, and then the Gauss representation is exactly functional. But let's say you can actually write down, it's easy to, or one example that's just purely in terms of the Galois theory, which is basically what happens if this is good ordinary reduction. But to give you sort of a picture, say this is isomorphic to chi1 star 0, chi2 epsilon bar inverse with chi I gp to k cross unramified characters epsilon bar equals mod p cyclotomic character, then this is finite flat, except unless chi1 equals chi2, and in that case, the star cuts out a Kummer extension. Next, you think with, so this is a Kummer extension that'll be like kp zeta p a to the 1 over p, where with the order of, let's see if I can squeeze this in here, order of pa not congruent to 0 mod p. So this is a situation where you don't get something finite flat, but in particular, if you chose A to be like a p-adic unit, like a unit in ZP, then this is going to give you something finite flat. Yes. No, because this is going to, yeah, so sorry, good question. So this is going to be a finite flat group scheme over ZP. So when we take to the generic fiber, we go over QP. It's now an Étale group scheme, and an Étale group scheme then just has a natural Galois action on it. And so that's what I mean. So the generic fiber is what gives you the action of this gadget. Okay, yeah. Just because that's my normalization, it's maybe not very good, but when you start doing things in higher rank and more generally, it's more common to use cohomological normalization. And in that normalization, instead of looking at the Tate module elliptic curve, you would look at its dual, which is the first cohomology group. So it's just that I want to set things up using the notation that's more common more generally. Although this is strictly speaking probably an incorrect definition, but it's just more in line with what I want to do later. Okay. Yeah. Yeah. Sorry. Well, sorry. What did you say again? Yeah. No, I'm looking at P, and I want, the thing at P. So I want to, my p-adic thing, I want it to be at P. Yeah. Yeah. No, I want the P equals P case so that there really is. Yeah. Yeah. Definitely. Yeah, it's a scheme. Yeah, absolutely. Yeah. Yeah, exactly. Because let me go back. I mean, something I had written here that doesn't exist anymore, right? Is that in the conjecture of Fontaine-Mazer-Langlands, one of the crucial things is you ask it be de Rham at places above P. So the thing that really plays the fundamental role is what's happening at P. And you can also see this in this dimension 1 example in the very top of the board here, right? If you try to understand like the L not equal to P contribution inertia, think about inertia in this completed group algebra. The L not equal to P stuff is some finite amount of data inside this maximal pro P completion of S. Think via class field theory, right? But then the part that's ramified at P, that's what's contributing the entire ZP rank of this thing. That's the part that's big. And that's the part that if we want to understand it in terms of like classical Hecke eigenforms or Hecke characters in the rank 1 situation, that we need to cut down. And we need to say, I'm not allowed any sort of p-adic character, but I really want things that are like, integral. Now, that being said, if you do want to try to relate things like big R universal, you might do so by trying to relate it to things like p-adic Hecke algebras acting on p-adic modular forms, something like that. So there is a role for that as well. Okay, any other questions? Okay, so then okay, back over there. Sorry? Oh, I mean, because, okay, so sorry. I mean, look at the splitting fields of this representation, right? This is a finite thing. So it's going to cut out, you're going to join the cyclotomic character. And then this upper triangular, it's so the diagonals act on exactly, if chi1 equals chi2, the diagonals act by on this upper triangular thing by the cyclotomic character. And that's going to give you a class in H1 twisted by 1 with FP twisted by 1. That's going to give you a Kummer extension. And so it's exactly, you know, this upper triangular thing is exactly the action on some like pth root of some element. Okay. Yeah, okay. So then when I get to this theorem for Ramakrishna, is that there exists a quotient R of R universal such that if B from R univ to A corresponds to some rho sub A with A Artinian, then phi factors through R if and only if the rho sub A restricted to GP is finite flat. And so that in fact there is a quotient of this thing that satisfies this universal property. So now I'm looking at all deformations of my rho bar such that it has this local condition. Okay, so this is going to be the R that we're going to consider. Okay, so now let's look at what T is. Okay, so again, set up as above. So univ, sorry. Yeah, sorry, it's pretty messy here. Slightly better there. This is pretty bad. Okay. All right, so now let's say I'm just going to use notation. I'm going to set this to be O. I'm just going to think of this as a formal polynomial ring in these variables for all primes not inside S. But then, I mean, really what I'm doing is I'm thinking these things as the standard Hecke operators that act on any sort of modular form you're used to, right? So TL acts by TL, SL by SL. So in particular, the eigenform G that I fixed at the start, so G, the eigensystem, gives you a maximal ideal M inside of TS. Okay, so, and let me just say some notation that's going to come up more importantly, maybe later, is we say M is non-Eisenstein if this rho bar, which remember is rho bar G iota, but I'm also some notation we'll also use is this is rho bar sub M because it actually only depends on M, is absolutely irreducible. And they just say this perspective of thinking of it not as a reduction of a mod P or a reduction mod P of some modular Galois representation, but rather it's just attached to the maximal idea of the Hecke algebra is particularly important when you want to start working over things like imaginary quadratic fields where things might have torsion. And it could be that this Galois representation maybe doesn't a priori come from something in characteristic 0. So now, right, Eichler-Schmor isomorphism tells us that if we look at cohomology of the modular curve, it looks like a copy of weight 2 modular forms, direct sum, another copy of the weight 2 cus forms, but maybe a slightly different complex structure, but that's not important. As Hecke modules. So I'm going to think of this as TS tensored over with iota to C, since my T I've defined to have p-adic coefficients. So then what happens, right? So what we do, let's say I'm going to let M. I'm going to instead consider this modular curve with coefficients in O, where now I can localize at this maximal ideal M. And my T, then that I'm going to consider is going to be the image of my kind of universal Hecke algebra inside the O endomorphisms of M. So if we have this, if I invert P, this is isomorphic to a product, it's a bit wider, I equals 1 to N, of some sort of p-adic fields that I'll call EF sub I with EFI equal to, this is just going to be the Hecke field over top of E generated by some new form. Sub I with Fi, a new form of level N, level dividing N, and weight 2. Yeah, thank you. I know, just give me 1 second. I was just going to try to, I was trying to just quickly get this and then raise it, but it's fair. Okay, and weight 2, congruent to G modulo whatever uniformizer for this field. Okay. Basically, what I'm saying is that this Hecke algebra acting on this thing is when I invert P, it's going to be just reduced, right? And it breaks up because of this isomorphism as just a product of eigensystems for some various new forms. So so what I say? Yeah.
Two meanings for the same N.
Oh.
One is there are N forms, and also there's AF.
Ah. Oh yeah. Sorry, you're right. Okay. So this will be an N. Okay. Yeah. I haven't said anything about that. Oh, you mean, sorry, here for this thing? It's just if this residual representation is absolutely irreducible. I mean, well, what I would say is if you look at, say, the traces of Frobenia, you want to see if they're not equal to some like character plus a character evaluated at Frobenia. I mean, it is so, you know, if you take some sort of cuspidal modular form, generically for sufficiently for, you know, all but finitely many primes, this residual representation will be absolutely reducible, but there could be some where, you know, it has some degeneracy. So it's just this condition. Okay. See what am I doing here? Now, okay, but then what we can do is I'm going to take the product of all the modular Galois representations, rho F I iota Fs to GL2 T 1 over P. Right, this is isomorphic to product equals 1 to M GL2 Fi. And for L not in S, the characteristic poly of this is it. Let me write this as rho Fi, yeah. Prob L is equal to the image of x squared minus TLX plus LSL. So this is an element inside T of X under the projection or the map from T to EI. Okay, so in some sense, right, these things have the same characteristic polynomial. It's just that you're mapping it via T to different things. So then at this point, apply a theorem of Carriel. So let me say you can assume, again, by the usual argument, this is contained inside the product from I to N, GL2 of the rings of integers. And so what Carriel tells you in general is that if A be a complete local Noetherian local, actually maybe we don't need that. Complete local ring with, say, residue field K, my fixed finite field, A contained in product from I to M, AI, a semi-local extension. With AI local, such, and let's say I take R prime equal to product from R I to M of R sub I, some representation to product goes on to M, GLN, A sub I. Okay, so this is exactly the sort of setup we have above with this Heck algebra. So this just means this local ring is contained inside some semi-local ring. Yeah, so, and I'm just writing it as a product of these local things. Maybe I want to assume it's a finite extension. Not sure if that's necessary, but let me say it's finite. Be a, just in case, AI finite. So it just means it's contained in some, it's, you know, this product of the AIs is some finite ring over top of A. And because it's semi-local, has finitely maximum ideals, it'll in fact just break up as this product because of completeness. Okay, and now let's see this representation continuous such that, and here are the two conditions I'm going to impose on it. So Ri modulo the maximal ideal of AI is independent of I. Okay, so they're all isomorphic to the same representation. And two, this is important, well, I mean, obviously, it's important. Trace of, independent of I, and sorry, the important assumption here, I want to assume it's absolutely irreducible. This is not true without this assumption. And then let's assume the traces of this R prime applied to GFS is actually contained in the subring A. Then R prime is conjugate to some representation valued inside GLN of A. This is the theorem. So what I'm saying is that you use the Eichler-Shimura relation to say that it's essentially just after extending scalars to C, but even you can then descend. Is that when you invert 1 over P, it's going to be a semi-simple E algebra, and a semi-simple E algebra, it's reduced. It's just going to be a product of fields. And the eigensystems of it exactly correspond to Heck eigenforms by some duality between Heck algebras and modular forms. Pardon? Yeah, absolutely. Yeah. Okay. Any other questions or comments? Whoa. Okay. Yeah. Yeah, probably. Actually, oh, I don't know. Actually, yeah, but yeah, I'm worried about that as well. But I don't know if this is in. Although one thing I've done is I've switched to using like rings to the groups, and I'm worried of that. But yeah, let's just do that for assumption. So yeah, thanks. Let me say. Let me put up here. Which I mean is fine for the assumptions I've set up, and say P is bigger than N. Yeah, thanks. Okay, so then here's the consequence. Is that if M is non-Eisenstein, then we get an honest to goodness, what I call rho sub M, Galois station valued in GL2 of this T width such that or L, say not dividing N, the characteristic poly, rho M prob L is equal to this Hecke polynomial on the nose. Squared. Oh, probably I wanted this. Sure. Yeah. Thanks. Yeah. Okay. And rho sub M mod M is my fixed rho bar. Okay. So I've produced a deformation of my rho bar valued in this Hecke algebra. And moreover, for any Q, minimal prime of T, QM mod Q restricted to GP as a map from GP to so what do the minimal primes give us in this situation? T mod Q, that's actually just going to be equal to, this is going to be the specialization to by one of these modular eigenforms, F sub I. This will be finite flat. And that's because these Galois stations constructed from weight 2 modular forms of prime level, they're constructed in Jacobians, right? And so they're given by some sort of abelian variety with good reductions. When you look at the torsion points, you get things that are finite flat. So this is going to satisfy this finite flat assumption. And so in particular, this is by local global compatibility. Well, by the construction for weight 2, this is nice. And TM is reduced. So that implies that rho M is finite flat in the sense that any Artinian quotient is finite flat. So at the end of the day, what we get is a map from our R to T. Right? We produce a deformation satisfying this problem valued in this Hecke algebra. So by just a universal property, we get a map. And it's surjective by the minimal polynomial star. So let me put star. These things are finite over ZB. So just the localization already, it's complete. Yeah. Yep. Oh, sorry. Did I write TM? Sorry. Thank you. Where did I put? Oh, yeah. Thanks. Yeah, I meant T. My T was already local. Okay. Any questions about this? Okay. So I want to say that what I've done here is this generalizes in a lot of situations. So in particular, if you think about things that are like conjugate self-dual automorphic forms for GLN, the types of things studied by Clozel, Harris, Taylor, and others, the same argument works. Nothing changes. You just have to consider some like higher rank automorphic forms, but really it's the exact same thing. Okay. However, it changes drastically if you want to go to something like an imaginary quadratic field, right? That's a completely different story. So, and that happens to do with the fact that implicitly I'm using here the fact that this Hecke algebra, this localized Hecke algebra, actually embeds inside of its T1 on P, right? The fact that it's ZP flat in particular, and then that we know all the local global compatibility for those factors in the product. Okay, any questions? Okay, so I think I'm out of time, so maybe I'll just end here. Yeah.